Swayam Prabha. Digital India. Educated India.
My name is Sankararaman. I have been in this department for the last 30 years or so. Recently, I retired and I am an emeritus professor now. I am going to talk to you about NMR spectroscopy. When I say NMR spectroscopy, most people will talk about structure elucidation. You run an NMR spectrum and interpret the spectrum in terms of chemical shift, coupling constant, and area under the peak, and arrive at the structure of the molecule using NMR spectroscopy. How many of you have heard about NMR spectroscopy? Quite a few have heard about NMR spectroscopy. It's good. My approach is going to be slightly different. I'm going to use NMR spectroscopy as a tool to understand dynamics of molecules. What do I mean by dynamics of molecules? If you take butane, N-butane as a molecule, the dynamic property it has is a carbon-carbon bond rotation. The carbon-carbon bond rotation gives you the eclipsed conformation, Gaussian conformation, and so on. Such a dynamic process can be studied conveniently by NMR spectroscopy. Another example is cyclohexane. What is the structure of cyclohexane? I have drawn the structure of cyclohexane. Is it a complete story? Is it a planar molecule? It is not a planar molecule, right? It is supposed to have a structure of a chair. How do we know it has a structure which is a chair type of a structure? From the spectroscopic technique we study, we arrive at the, if it is a planar structure, all the 12 hydrogens will be identical. Whereas if it is a chair structure, this is called the axial hydrogen and is the equatorial hydrogen. So there is a difference between the two hydrogens which are located, and if NMR spectroscopy can tell us there are two types of hydrogen in cyclohexane, that is sort of a proof for the structure of the cyclohexane in the chair form. Not only it is so, when you have a, let us say, bromine present in the system, now this molecule can undergo dynamic process to go from one chair form to another chair form. Here, for example, upon flipping the chair from one chair to another chair, you are going to make the bromine axial to equatorial and the hydrogen from equatorial to axial. Now, axial hydrogen and equatorial hydrogens have entirely different chemical environment, so that NMR can distinguish the two and tell two different chemical shift arises out of the. Later on, you will get an assignment from the coordinator, and in that assignment, one of the question is how do we determine the ratio of these two conformers? These two compounds are in equilibrium, and the equilibrium constant can be easily determined by NMR spectroscopy by varying the temperature of the probe of the NMR. With this short introduction, let me move on to the tau talk. The study of dynamic properties of molecules What I mean is conformational changes. This is a conformation. This is another conformation. The conformational change is given by the equilibrium constant. Restricted rotation along the CC and CX bonds. This is another dynamic process one can study. Aggregation phenomena. Molecules tend to aggregate and they give NMR pattern differently from the monomeric species. Such aggregation process can be studied. Fluxional molecule. Molecules which are fluxional in nature. I'll give you an example of that. This is called Barber lane. This is one of the fluxional molecules, so much so that this has a symmetry cutting across the carbonyl functional group. If you have an imaginary atom here, it cuts through that atom also. It has a plane of symmetry. That plane of symmetry gives a feature in the NMR which is easy to identify and then arrive at the fluxionality of this molecule. The reason we are able to use the NMR for dynamic processes are dependent on two parameters. One is the temperature, the other one is concentration. The dynamic process equilibrium usually is affected by both temperature as well as concentration. If you have a control over temperature as well as concentration, then it is easy to do the NMR spectrum. It is possible to record an NMR spectrum in the temperature range of minus 150 degrees Celsius to plus 150 degrees Celsius. A 300 degree window is available for studying the spectrum, and most organic compounds, the fluxionality and the dynamic processes are confined within this temperature range. So it is possible to record NMR spectrum at these temperatures, provided your solubility is not a problem, provided your solvent doesn't freeze during the course of the measurement. These are the two restrictions, experimental restrictions you have. Otherwise, theoretically, it is possible to study NMR spectroscopy in this temperature region. So this temperature region gives you an access to the activation barrier typically in the range of 8 to 25 kilocalories per mole. The dynamic process has an activation barrier. The chair form, one form going to another form has an activation barrier of about 10 kilocalories per mole. How do we know this? From the NMR spectroscopy study, we know this. So this temperature range will allow you to study processes which are occurring in an activation barrier of about 8 to 25 kilocalories per mole. If it is below 8, you will not be able to study by NMR spectroscopy because it is too fast to happen. If it is above 25, it will be too slow. You don't need NMR spectroscopy to study this. So these are the limitations that we have with the dynamic processes. Now let us assume the proton can exist in two possible chemical environment. Now NMR spectroscopy is all about nuclear spin and the effect of nuclear spin on the environmental magnet, laboratory magnet, or the laboratory magnet effect on the spin of the nucleus. Proton has a spin of half integer. So it is easy to study the proton NMR spectroscopy because I is equal to half. When I is equal to half, it can take two positions. One is aligned with the external magnetic field. The other one is opposed to the external magnetic field. And that gives a transition which is a Zeeman splitting transition. And the transition is what is seen as an NMR spectrum giving a line in the absorption scale. Now, for NMR to distinguish two protons, you essentially need the two protons in two different chemical environment. What is chemical environment? Chemical environment is nothing but electron density. Chemical reactions are triggered by electron densities. So if you have two different electron densities, then the external magnet will have its own effect and you will get two different peaks in the NMR. The ability to clearly define the chemical environment of a proton and hence the chemical shift will depend upon the resonance time of the proton in that particular environment. So how long is the proton going to stay in the axial position or equatorial position? What is the time duration for which this equilibration can exist? And this is something one can study by NMR spectroscopy. The energy difference between the two states is very, very small. For example, when you talk about axial hydrogen and equatorial hydrogen, the chemical shift difference is only about 0.5 ppm or so. 0.5 ppm will correlate to something like 10 to the power minus 7 calories per mole. And therefore, the lifetime of any particular state should be sufficient for NMR to record at chemical shift wise. This is the uncertainty principle relating the lifetime and the energy gap between the two states. If the lifetime is finite, then you will have a delta E which is going to be lower, and hence the uncertainty principle applies to the NMR spectroscopy in this format, not in the normal format of momentum versus position. Normally you study the uncertainty principle in momentum versus position, right? The position cannot be determined accurately when the momentum is. Here it is the lifetime versus the energy relationship, which is uncertainty principle relationship. If a proton is exchanging very fast between two states, NMR will give only an average chemical shift. So if you record the NMR spectrum of bromobenzene at room temperature, the hydrogen is going to be neither in the axial position nor in the equatorial position because it is too rapidly interconverting. Otherwise, this equilibrium is very fast. So you cannot distinguish between the axial hydrogen and the equatorial hydrogen. So NMR will not be able to distinguish it will give only the average value of the two positions of the. If a proton exchanges between too slow, then NMR will see the individual states. It will give you the one peak for the hydrogen, which is the axial position, and one peak for the hydrogen in the equatorial position. The rate of such chemical process is controlled by varying temperature and hence the usefulness of variable temperature NMR. Study some conformational dynamics using NMR spectroscopy. Now this compound is a D11 compound. Only one hydrogen is left in cyclohexane, so that you can conveniently study one hydrogen to be either in the axial position or in the equatorial position. And all the other hydrogens are replaced by deuterium. When you are observing NMR of proton, you will not see deuterium. That is the advantage of this experiment. So somebody has bothered to synthesize the D11 compound of cyclohexane and measured NMR spectrum of the compound at various temperatures. Now, at a low temperature of minus 89 degrees Celsius, two peaks are observed and reasonably sharp peaks are observed. The sharpness of the peak has something to do with the lifetime of the proton in the chemical environment. In other words, the uncertainty principle is applied here. Here the two states are clearly visible. That means the process is extremely slow here. So as a result of this, The equatorial hydrogen and the axial hydrogen are nicely seen in the NMR spectrum. And as you increase the temperature, at a particular temperature, coalescence takes place. And the coalescence temperature is around 60 degrees or so, 61 degrees or so. And beyond that temperature, it becomes sharper and sharper. And eventually, it becomes a sharp single peak is seen for the axial and the equatorial hydrogen. It is because of the fact that the axial and the equatorial hydrogens are no longer distinguishable. The rapid equilibrium becomes rapid, so NMR cannot distinguish the two. Here equilibrium is very slow, NMR can very easily distinguish the two. And in between you have the uncertainty principle operating in terms of not being able to. It is like, for example, taking a picture with a slow camera, what you see is a blur. You don't see the accurate images of the. So this region is similar to that, a slow camera operating on the fast moving object. Here is another example of a dynamic process. This molecule is interesting because it is a chiral molecule. When I say chiral, what do I imply? Pardon me? 4 different groups. That is a chiral carbon. Non-superimposable mirror images. That is the correct answer. It doesn't have to be a molecule. It could be a donkey. A donkey can be chiral donkey if its mirror image is non-superimposable on top of a original donkey. Right? So when you say chiral molecule, your answer is acceptable at the 8th standard level. A carbon with 4 different groups attached. But as you go to higher and higher studies, your answer has to be more sophisticated answer you have to give. More accurate answer you have to give. More general answer you have to give. This molecule is chiral, but see what happens when it flips from one form to another form. It forms a mirror image of the chiral compound. These two are mirror images. Are you able to see the mirror image relationship? If I put a mirror, right, cutting across the arrow here, reversible arrow here, this will be a mirror image of this. So this molecule is not only chiral, it undergoes racemization by the dynamic process of going from one chair form to another chair form. So in between stage is what NMR will see, and that is a frozen state which is here, low temperature, minus 223 Kelvin here. In the frozen state, how many NMR signals you will see? This is carbon NMR. I am not talking about proton NMR. So carbon 13 also has a magnetic moment, and it is a spin-off nucleus. So if you have 10 different carbons in 10 different chemical environment, you will get 10 peaks, right? Because this molecule is chiral, it will have all the carbons in different chemical environment. That is the definition of a chiral molecule. So it will give 8 peaks, 6 peaks corresponding to the ring carbon, 7 axial carbon, 8 equatorial carbon. So you see the 8 peaks are there or not? Can you count here? 1, 2, 3, 4, 5, 6, 7, 8. NMR doesn't lie. 8 peaks means 8 peaks are there in the spectrum. Unfortunately, these 2 peaks are overlapping with top of each other. Nevertheless, the slight hint is there that there are 2 peaks here. So 8 peaks can be accounted for. If it is rapidly undergoing interconversion at a higher temperature, NMR is going to see an average structure to be a planar structure, an achiral structure. So this is a structure is what NMR will see if it is rapidly undergoing. In this structure, these carbons are neither in the axial position nor in the equatorial position. They are in the planar cyclohexane type. structure with the two methyl groups cis to each other. So if you have this structure, and how many peaks NMR will see? This has a plane of symmetry, remember. So anything above is same as anything below in terms of chemical shift value. 4 peaks you will see, right? 1, 2, 3, 4. You see 1, 2, 3, 4. 4 peaks are seen there. And in between, of course, you have the uncertainty principle operating, and you have the broadening, coalescence temperature, everything comes into picture. So this is a nice example of a molecule to be chiral or not. NMR sees this molecule as a chiral molecule provided there is no rapid interconversion. It sees it as an achiral molecule when it is a rapidly interconverting equivalent. Racemic mixture is what is you have there. Now, while doing the variable temperature NMR study, you gather a lot of data, and this data can be utilized to obtain the rate constants of the dynamic process. Not only rate constant, it can also apply to get the thermodynamic parameters of the system. For a simple system with the coalescence temperature kinetics, single point kinetics, this is pi delta nu by square root of 2. Delta nu is the difference in the chemical shift value of the 2 hydrogens or 2 carbons we are talking about. The axial equatorial carbon in the dimethyl cyclohexane, or the axial equatorial hydrogen in the cyclohexane itself. That is the delta nu that we are referring to. This is a single point kinetics. Nevertheless, it is useful to obtain the rate constant by using this kinetics. Or if you want to do an elaborate study, you can do modeling, not modeling, you can do calculation of the NMR spectrum and arrive at the calculated spectrum and look at the similarity between the calculated spectrum and the experimental spectrum. Here there are molecules which oxygen and sulfur are located in this position. So all the 3 axial hydrogens are equivalent, chemically equivalent. That is a red color one. I can put red color one here as well as here. They are all equivalent, chemically equivalent. The blue ones are also chemically equivalent. I can put a blue one here and blue one here. That will be chemically equivalent. So there are 2 sets of hydrogen with each having 3 number of hydrogens. In this case, the slow exchange process, in other words, at low temperature, when there is an interconversion is slow, what happens is the axial and the equatorial hydrogens are seen separately. So the axial hydrogen and the equatorial hydrogen, what is the relationship, stereochemical relationship? Look at the chemical environment of the axial hydrogen and the equatorial hydrogen. They are entirely different. This is axial position and this is equatorial position, right? So they have to be diastereotopic in nature. They cannot be isochronous, meaning the same chemical shift will not be there because the chemical environment is different. They cannot be also chiral. They cannot be also the same chemical environment, same chemical shift value, for example. It's not possible. 2 different chemical shift value means they are diastereotopic in nature. The diastereoisomerism is what is seen here. What was originally axial hydrogen becomes equatorial hydrogen. What was originally equatorial hydrogen becomes axial hydrogen. So it gives a AB signal, AB quartet signal in this particular compound, these 2 compounds. And in the slow exchange process, it gives a AB quartet, and the fast exchange process, it gives a singlet. Fast exchange process, you cannot distinguish between the axial and the equatorial position. So it is the barrier for flipping of the trioxane molecule is about 10.9 kilocalories per mole. It is a piperidine molecule. Here you have 2 sets of AB quartets. This is one AB system and this is another AB system. In between, you have substituted deuterium in these positions. So they will not account for the. You see two AB systems here. What do you mean by AB system is? A is split into a doublet and B is also split into a doublet mutually. That gives a AB quartet, which is a 4-line pattern. And the 4-line pattern is what you see here, 1, 2, 3, 4. This is for the ortho, not the ortho, 2 and 6 positions of the piperidine. And this is for the 4th position of the piperidine. This is the 4th position, is this position here. So these two hydrogens come in this chemical shift region. And these two hydrogens, 4 hydrogens in this position come in the chemical shift value, which is higher than the here. So as you increase the temperature, what happens is rapid equilibrium takes place, and as a result of that, you get a singlet. The AB quartet coalesces to a singlet. The coalescence temperature is somewhere here between 65 and 62.5, and that is a sharp singlet you see when it is rapidly undergoing equilibrium. Now we look at the spectrum of these two compounds. This is a anti-conformer of the molecule, and this is a Gaussian conformer of the molecule. These are conformations, right? Conformations. And these two methyl groups, what do you think is the chemical shift value of these two methyl groups? Will they be identical or will they be different? Why you say identical? Pardon me? There is a symmetry element which is C2 axis of symmetry passing through this line here, and that will rotate C2, it will bring the methyl up and this methyl down. So the two methyls are related by a symmetry operator, and so they are equivalent, they will give only one peak in the NMR, right? Similarly, if you take this two methyl peaks here, again this is symmetry related by the plane of symmetry, which is this one, sorry, C2 axis of symmetry. So these two are also symmetric in nature, they are same chemical shift value will be there. So if these two conformers are present in solution, as long as they don't interconvert each other very rapidly, you should see two signals, one signal for this conformer, the other signal for this conformer, correct? And if I take integration of the let us say, for example, I have one peak for the Gaussian conformer and another peak for anti-conformer. This is possible only when you do it at low temperature, -44. And it says it is 2:1 ratio. Area under this peak is 2:1, so let's make it bigger. What does this 2:1 ratio imply? What does it imply? The concentration of the anti-isomer is twice as much as the concentration of the Gaussian isomer. You studied in stereochemistry, Gaussian isomers are less stable than anti-isomer because of the steric hindrance. With this one, the two methyls are far away from each other compared to here. And moreover, here all the chlorines are coming together one after the other, so it is unstable. So relative stability wise, this is more stable and this is less stable. So that should reflect in the population of the two conformers in solution. So this 2:1 ratio is actually the ratio of the conformers population in solution when it is measured at 44 degree centigrade. So it is another question that is asked in the assignment. How will you determine the ratio of these two compounds in solution? You record the NMR spectrum at a sufficiently low temperature so that the axial hydrogen and the equatorial hydrogens come in different chemical shift value and they will appear as a two-line pattern. I am putting it as a multiplet here because of the adjacent hydrogen which is going to split the hydrogen under observation. So if you see a spectrum like this, you can integrate the spectrum. Integration is the height of this peak here. Let us say this is L1 and this is L2. L1 by L2 will be the ratio of the two compounds, two conformers in this particular. You understand? Is anyone here who did not understand what is being said in the last 1 minute? Everybody understood. I am happy about it. Here fluorine is used as a probe for the NMR. Fluorine 19 is again spin-half molecule, spin-half atom. So the fluorine spectrum is what is seen here. These two fluorines are again same equivalent. These two fluorines are also equivalent. These two fluorines are also equivalent. So you will see three peaks in the NMR if all the three are present in solution. And based on the calculations, you come with the answer 9.9 kilocalories per mole by FT-NMR, fluorine NMR in this particular case. Here, tertiary butyl cyclopentane, you look through the molecule along the carbon-carbon bond axis, which is a sterically hindered position in terms of restricted rotation. So restricted rotation means this will be one of the conformations with two methyl groups equivalent and one methyl group distinctly different from the other two methyl groups. So you see two resonances, 2:1 ratio, 2:1 corresponding to the two methyls here and one methyl here. The integration of this will be 2:1 ratio. And this will be the conformation that is seen by the NMR. Tryptosine is an interesting molecule. This is a propeller shaped molecule. Can you see the propeller? If I put an axis along the carbon-carbon bond, if I put a line across the carbon, which is a bridgehead carbon here, that is a C3 axis of rotation, and C3 axis of rotation gives the propeller shape for this molecule. As a cartoonic representation, because benzene is a planar ring, I have put this as a cartoonic representation of the same molecule. Now this molecule has a steric crowding around this area where the three of the hydrogens is trying to stop this rotation of the carbon-nitrogen bond because of the steric hindrance. So this will be CN bond rotation as well as nitrogen pyramidal inversion are the two processes one can study here. If you look at the molecule, this molecule here, this is a chiral molecule. Nitrogen has three different substituent and it fits the definition you gave some time back. So it is a chiral nitrogen molecule, chiral amine in other words. Because it is chiral amine, these two hydrogens are going to be diastereotopic in nature. This is a chiral center and this is adjacent prochiral center. Prochiral centers are usually diastereotopic relationship will be there. The two hydrogens will come separately in the NMR spectrum. So indeed the two hydrogens come separately in the NMR spectrum. Each has a doublet. AB pattern is what is seen here. This is on higher temperature where the rotation becomes faster and faster. You have a broadening of the signal, and then finally sharpening of the signal again takes place at minus 49. This temperature rapid rotation is taking place, and that is why it is giving a sharp peak here. This is a calculated spectrum, simulated spectrum. The simulated spectrum looks nearly same as the experimental spectrum, except for the noise here, which is artificial noise here. So this is a rate constant they have plugged in to do the calculation. From the rate constant, you can get the thermodynamic parameters, and these are the thermodynamic parameters that they got in the two compounds that we are dealing with. The activation barrier is something like 11.6 kilocalories per mole for the benzyl compound, and for the methyl compound it is 9.2. This compound it is 9.2 kilocalories per mole. This is another molecule where the carbon 13 spectrum is used in this particular instance. The carbon 13, you see this carbon, quaternary carbon, there are 3 such carbons here. And these 3 carbons are entirely different in terms of the chemical shift values of this carbon. And here you will see backside carbon also is distinctly different from each other. So the backside carbon comes as a 3 carbon signal, and the front side quaternary carbon comes as a 3 carbon signal. Totally 6 peaks are seen here. The 6 peaks, sharp peaks are seen here essentially because of the 6 quaternary carbons which are distinctly different from each other. So it gives 6 peaks in this region. And when it is fast rotating, you see only 2 carbons here, only 2 carbons are seen here. And as a result of that, you have the 2 carbons, one belonging to the front side carbon, quaternary carbon, the other one is back side quaternary carbon. So they are different for the different environment. What are annulenes? Annulenes are conjugated cyclic molecules, right? Alternating double bonds. Benzene is a 6 annulene. This is a 18 annulene. This is a large cycle. Annulene is a large annulene, and it can undergo rotation of the carbon-carbon single bond to bring this hydrogen outside and this hydrogen inside. So that is a dynamic process one refers to here. For example, if the molecule is frozen at low temperature and record the spectrum, how many different peaks you will see? All you have to do is find out how many types of hydrogens are there. There are 2 types of hydrogen. One type of hydrogen is outside the ring, other type of hydrogen is inside the ring. Now the hydrogens which are inside the ring, what is special about them in terms of chemical shift value? Their chemical shift value will be in the negative value because they are highly shielded electron density wise. This is high electron density cavity, and these hydrogens are in the cavity of the 18 annulene. So as a result of that, they will be highly shielded. So the chemical shift value will be in the negative scale, minus 4 point something or something. Whereas the outer hydrogens will come at a higher delta value, 9 point something or so. 9.4 or so is the chemical shift value of the 12 hydrogens of the outer hydrogen, and 6 hydrogens of the inner hydrogen comes at negative value. You can see here. In between temperatures, you have the uncertainty principle operating, so much so that if you get at plus 40 degrees, you don't see a spectrum at all, even though the compound is there. This is because NMR is unable to determine whether the hydrogen is inside or outside at this temperature, at this rate of interconversion. So NMR just gives you a flat line, it doesn't give you any peak at all. The uncertainty is so much so that it is spread into, as you take a peak and make it larger and larger. Let us say you have a peak initially like this, finally it is collapsing into a baseline. And that baseline is what is seen here in the spectrum, plus 40 degrees centigrade. So this is an example of a 18 aniline undergoing interconversion of the peaks which are interior and peaks which are exterior. Can I go further? Here is another example of a strained molecule. Why is it the molecule strained? Where is the strain coming from? What is the strain due to? Solunga, you want to say something, you can tell. The triple bond in a cycle is not allowed, right? Because triple bond is supposed to be sp hybridization, linear hybridization. So it has to be a line, it cannot be a bent line and things like that. So you are right, the triple bond is responsible for the strain in the molecule. So the molecule adopts a conformation which is this conformation. This carbon goes up and this carbon comes down. So it is non-planar now. When it is non-planar now, when there is no plane of symmetry, it is a C2 chiral object. It's a chiral molecule. And when it undergoes the chair to chair type of interconversion, it's not really chair actually. It's a flipping of this ring down and this ring up, carbon up, gives this particular conformation. When there is a rapid interconversion between these two conformations, NMR will see only a singlet, 145 degrees centigrade. NMR sees a singlet because it sees the planar structure. Whereas at minus 58 degrees centigrade at room temperature, above room temperature, it is appearing as a AB quartet. AB quartet is what is seen here. All right. NN dimethyl acetamide. This you must have seen somewhere in the spectroscopy course. Did you have a spectroscopy course? Did you have a course in spectroscopy? NMR spectroscopy? No? No. If you take this molecule and measure the NMR spectrum, you should get one peak for this methyl, another peak for this methyl, and one more peak for the hydrogen. Correct? 3 peaks you should get. One peak for this methyl, other peak for this methyl comes as a 2 singlets here, and one peaks for the hydrogen is not shown in the spectrum. This is a methyl region is what is seen here. The other region is not recorded in the spectrum here. This hydrogen come as a 2 singlets, and as you increase the temperature, it becomes a singlet. Both the peaks coalesces at 114 degree, and it comes as a sharp singlet in the spectrum. The activation barrier is about 22 kilocalories per mole. What is the dynamic process here? Dynamic process is carbon-nitrogen bond rotation. Carbon-nitrogen bond rotation is restricted here. Why is it restricted? Because of the carbonyl group has a double bond character. The carbon-carbon bond has a carbon-nitrogen bond has a double bond character. You can see here double bond character of the carbon-nitrogen bond. So the rotation along the carbon-nitrogen bond is restricted, and as a result of that you see two peaks, because this methyl cannot exchange at that temperature. Two peaks are seen here at room temperature, and as you heat the sample it becomes faster and faster rotating, and these two becomes indistinguishable. Are you able to see it? This is a simple nitro compound, trinitro N-methylaniline. Again, CN bond rotation is what is seen here. Now you have to tell me why there is restricted bond rotation in this molecule. Nitro group is electron withdrawing. So what? Because of conjugation, through conjugation, this nitrogen lone pair is delocalized onto the nitro functional group. That gives a double bond character for the N double bond here. That puts the hydrogen here and the methyl here. Now these two hydrogens are equivalent when there is no restricted rotation. When there is a rapid rotation, these two hydrogens are equivalent, right? When there is restricted rotation, these two hydrogens are not equivalent. So they should couple with each other and give a meta coupling. The meta coupling is what is seen here as a doublet. You can see here as a doublet of doublet. AB quartet is what is seen here. AB quartet is seen at minus 60 degrees when there is a restricted rotation, and around minus plus 36 degree room temperature spectrum you see a sharp singlet. Because of the rapid rotation of the carbon-nitrogen bond, these two becomes equivalent and it gives a singlet here. This is a simulated spectrum, calculated spectrum. So you can see here in the calculated spectrum nicely the singlet and the AB quartet for these two. The meta coupling is what is seen here as a these two hydrogens will appear at the same chemical shift value when it is HA and HA. The reason I have given the A subscript is to identify this as the same hydrogen. Whereas when restricted rotation is very slow, this is going to be B and this is going to be A. So A2 system becomes an AB system here. A2 system is a singlet system. AB system is a AB quartet system. So this is how you distinguish the two conformations. Molecular rearrangements. You must have studied some molecular rearrangement. Can you name some molecular rearrangements? Say it louder. Pinnacle rearrangement. Good. What else? Benzidine rearrangement. Have you studied cope rearrangement? What is cope rearrangement? Very good. 3,3 sigmatropic rearrangement is cope rearrangement. Can somebody come and write an example from the blackboard? Doesn't matter if it is wrong, we will correct you. Pardon me? Come and do it. Come, don't be shy. White chakra. When you are a teacher, you should write legibly so that the students understand what you are writing. What did you say? 1, 5?
1,5 dyene.
So number is 1 and 5. I don't see the fifth carbon.
3, 3 break for percent. Sigma 3, sigma 2.
First, write the starting material structure properly. Then you can. 1,5 diene, you have said.
Yes.
You write the structure of 1,5 diene. Number the 1,5.
So 1, 2, 3, 4, 5.
1,5 and 1,4 தானே இருக்கு அதுல. It is same, 1,4 only. 1,3 actually.
Oh.
1, 2, 3, 4, 5. 3, 3
breaks.
1, 2, 3. 1, 2, 3. Breaks here. You know the answer, but you are not able to. Such mistakes you should not make in the examination. Please go ahead. Thank you. Here, can you see the 1,5 diene? You have studied bulvalene? No? This is an exotic molecule, most notorious molecule that is ever seen. Bulvalene is a fluxional molecule, undergoes co-prearrangement, degenerate co-prearrangement. When it undergoes, one of the beauty about the co-prearrangement is the product is same as the starting material. So it is a degenerate rearrangement. When the starting material and products are same after rearrangement, it is called a degenerate rearrangement. Originally, it was proposed in 1962, even before the molecule was known. Somebody proposed that it is going to be a fluxional molecule. It is going to undergo molecular rearrangement. Synthesis was done 1 year later, 1963. It is a C3V symmetric molecule. Can you identify the C3V symmetry? C3 symmetry? C3V symmetry. Imagine a point here. Imagine another point here in the center of the triangle. Draw a line from that point to this point. The 3 vinyl groups are mutually exchangeable by the C3 operation. When I do a C3 operation, how many degrees am I supposed to rotate? 120, right? 120 rotate, this will come here, this will go here, and this will come here. Are you able to see it? C3 axis of rotation makes it C3V symmetric molecule. What is interesting is it can make 1.2 million times it can undergo co-prearrangement, different co-prearrangement, and still produce only bulvalene. So 10 factorial divided by 3 comes from the fact that it is a C10 molecule. There are 10 carbons and hydrogens which are identical. Divided by 3 because it has threefold axis of symmetry, it reduces 1/3 of the number that you get in 10 factorial. So this many number of bulvalene molecules can be synthesized by rapidly interconverting co-prearrangement. What is the co-prearrangement in this molecule? You see here 3,5 is a triangle based carbon. After undergoing co-prearrangement, three five is opened up, right? And 310 is now opening up. See, 310 opened up to give 410. So you can make the bulvalene undergo the co-prearrangement repeatedly, reproducing itself in each of the co-prearrangement. So this molecule cannot be destroyed basically. If we heat it, it will go to itself through a co-prearrangement. What is interesting about this molecule is when it is undergoing co-prearrangement very rapidly, NMR cannot distinguish the different hydrogens. All the hydrogens will appear as a singlet. It is because at what point of time once it was a cyclopropane hydrogen that becomes vinylic hydrogen upon rearrangement, and what was vinylic hydrogen becomes a methane hydrogen. This is a methane hydrogen. So all the 10 hydrogens become equivalent at the temperature of 120 degrees centigrade. So it gives a sharp singlet at 120 degrees centigrade. At minus 85, what happens is the vinylic hydrogen, 6 hydrogens are seen here separately, and the cyclopropyl hydrogen and the methane hydrogen come as unresolved multiplet here around 2 ppm or so. And this is TMS. TMS is tetramethylsilane. In between, you see mountain kind of a spectrum is what is seen here. This is because of the uncertainty principle of the hydrogen residence time in each of the conformations. This is a 100 megahertz spectrum. This is a 60 megahertz spectrum. This is a 100 megahertz spectrum. That is the only difference. Otherwise, the number of peaks are all same. This is a carbon-13 NMR spectrum of bulvalene. Now tell me how many carbon-13 signals you will see when it is not rapidly undergoing rearrangement. When it is not undergoing rearrangement, how many peaks you will see? All you have to do is count the number of carbons which are different from one another. C3 axis of symmetry is there, so you have to do only one, 2, 3, 4, 5, 4 peaks are seen. This becomes a part of the triangle. So 4 peaks you will see. 1, 2, 3, 4 peaks only you will see. And when you heat it up, when all the 10 carbons become equivalent, you will get a singlet. You just see a singlet here. These peaks are due to TMS and DMF solvent here. This is due to DMF solvent here, right? So the 4 peaks are 1, 2, 3, 4 peaks are there. There are 2 peaks here. Third and fourth peaks are here. This is another bicyclic system which is undergoing co-prearrangement. In this particular case, the diazine is a compound. This is what NMR will see under very fast rapid rotation, rapid interconversion. This is what NMR will see. Under slow conversion, this is what NMR will see. So this is a to B C system. This is a to B2 system. Spin label wise, if I label this will be A, this also will be A, this will be, and this also will be B. Whereas here it will be A, B, C2 or A to B, C. A, B and C. Are you able to see it? What about in this side? Are you able to see this number of peaks that you will see? Yes? This is again another aniline, methanoaniline. The methanoaniline case, this spectrum of the compound here, you will see essentially 1, 1, 2, 2. AB pattern is what you will see in the NMR spectrum. AB pattern is what you see in the spectrum. Okay. Under frozen condition, minus 138 degrees Celsius. Is it minus or plus? Minus. You see a frozen spectrum of this compound. The dynamics is not very fast, it is very slow. So you will see this as a separate AB and this as a separate AB, because this hydrogen is above the triene portion of it. This hydrogen is above the diene portion of it. So these two hydrogens are no longer similar. Here this hydrogen and this hydrogen are same, this hydrogen and this hydrogen are same, right? Whereas here these two hydrogens are not same and these two hydrogens are not same. So you see 2 AB pattern. 2 AB pattern is what is seen here. 8 line pattern is what is seen here. 1, 2, 3, 4, 5, 6, 7, 8. 8 line pattern is what you will see here. And 2 AB pattern is what you see here. How many of you heard about George Wohler? No? He is a Nobel Prize winner in chemistry several years back. He proposed this kind of a structure for norbornene cation. Norbornene cation is this. This is norbornene cation. This is generated by taking the chloride and ionizing the chloride. You get this cation. What is interesting about this cation is this is a unconventional cation. This is here there are 4 carbons, so 3 carbons and 4 hydrogens are accommodated here. Why 4 carbons? sorry, 3 carbons and 4 hydrogens. There is 1 hydrogen here, 2 hydrogens here and 1 hydrogen here. Non-conventional delocalization of electrons in this particular structure. These 3 methylene groups are identical to each other. This methane is identical to each other itself, unique to itself, and these 3 are identical to each other. George Ola proposed the structure of the norbornene cation to be this one based on the NMR. So here you must see 1, 2, 3 protons you should see. Sorry, 6 protons you should see. 2 plus 2 plus 2. 6 protons are there. 6 hydrogens are there in this peak here. And this one is a magenta, only 1 hydrogen is there. 1 hydrogen is there. This has 4 hydrogen. 4 hydrogens are there. So it proves the structure of the compound to be not localized like this. Delocalized structure is what is seen here in this particular system. 3 carbon, 4 hydrogen centered bond is what is seen here. That is seen by the 3 peaks here. Otherwise, the spectrum is complicated if it is one of these structures. There are more non-equivalent hydrogens in these structures than in this structure. That is the reason it's like this. Organometallic compounds can be studied by variable temperature NMR spectroscopy. Here what happens is the tetracarbonyl ion goes between these 2 bonds, 2 double bonds in an alene structure. Alene is perpendicular to each other, the carbons, right? So these 3 carbons are in one plane and these 3 carbons are in another plane perpendicular to this plane. So if the molecule is going to, if the ion carbonyl is going to shift from this position to this position, originally this position, these 2 methyls are equivalent methyl, and these methyls are different methyls in terms of spectrum. Chemical shift difference will be there in this methyl. Whereas in this particular compound, these 2 methyls will be equivalent and these 2 methyls will be non-equivalent in the nature. So you should see 2 methyl peaks and 1 methyl peak, 1 6 hydrogen peak in the NMR spectrum. At higher temperatures, room temperature for example, the interconversion is so rapid that you see only 1 signal. This is at plus 30 degrees centigrade and this is minus 60 degrees centigrade. So these are the 2 types of migration you will have. Such migration can be studied by eta 6, eta 4, all kinds of carbonyl compounds. These are examples of studied by NMR spectroscopy to determine the activation barrier of the rearrangement. In this case, the spectrum goes from an eta 1 to eta 5, versa versa, eta 5 to eta 1. You know what is eta 5, eta 1 and so on, organometallic. Hapticity. Yeah. The hapticity here is 5, hapticity here is 1, right? Eta 5 and eta 1. When it undergoes rearrangement, the eta 5 goes to eta 1 and eta 1 goes to eta 5. That means in between temperatures, you will not see either eta 1 or eta 5, you will see only eta 5. So the spectrum becomes a singlet, all the 10 hydrogens in the molecule becomes equivalent and it becomes a singlet molecule. Whereas if it is this molecule, then it is HA, HB, HC, HA, HB, HC. The 3 different types of hydrogens are there and these 3 different hydrogens are seen here. And this pattern is very characteristic pattern for the double bonded system like this with 4 hydrogens. This HA is this particular hydrogen. Trimethyl aluminium is a pyrophoric compound. Pyrophoric compound means it will spontaneously catch fire under atmospheric conditions. It can be handled under nitrogen argon condition, and you can study the dimerization of aluminum. This is a bridged methyl system. This is a terminal methyl system. Bridge methyl is abbreviated by B, terminal methyl is abbreviated by T, BT, bridge and terminal. How many terminal hydrogens are there? 12 numbers are there, right? How many methyls are bridged one? 6. So 2:1 ratio, you should get peaks. 2:1 ratio, you have the peaks here. 6 hydrogens terminal and 6 hydrogens, 12 hydrogens terminal and 6 hydrogens bridged. When it is undergoing a dissociation, all the methyls become equivalent. This is a planar trigonal molecule, and this will give 9 hydrogen peak, single peak here. Single peak of 9 hydrogen intensity is what is seen here. Methyl alcohol spectrum. What do you expect for methyl alcohol NMR spectrum? Single peak for the methyl and one peak which is broad peak for OH. This is normally what is seen in the NMR spectrum. But that will depend upon the purity of the solvent, methanol purity, and the temperature at which it is measured. See, at room temperature what you said is correct, singlet for the OH and singlet for the methyl group. But this is a equilibrium which is rapidly occurring in the proton NMR spectrum of the methyl group. That is the reason you see a singlet or the 2 hydrogens. There is an uncertainty as to where the hydrogen is located, whether it is in this oxygen or in this oxygen. So the hydrogens are color coded to show that the exchange is taking place between this methyl and this methyl. So when you cool it to minus 65 degrees centigrade, when this is cooled down quite considerably, minus 65, the exchange process is not taking place. So the NMR will see the methyl attached to a OH hydrogen that will split the CH3 into a doublet, and the CH3 will in turn split into a quartet. So quartet is the OH and the doublet is the methyl group that you see here. Is it clear? What was originally not coupled now becomes coupled because of the slowness of the deprotonation reaction that is taking place. Now, you will get an assignment I have given to the coordinator. I don't know whether it is already there in your packet. It's not there. He will give you. If you find it difficult, it is okay. You can come to my office and discuss with me. Whatever difficulty you may have, I will be able to solve it and give you the answer. But in the process, you should learn to deal with the problems. That is the reason that problem sheet is given, assignment sheet is given. Normally, NMR spectrum, you give the data and ask you to arrive at the structure. But here you are not asked to arrive at the structure, you are asked to calculate the equilibrium constants and things like that based on the variable temperature NMR. Okay? So feel free to come to my office. My office is in the new building, which is adjacent wing building. And it is in the ground floor near the lift, room number 150B. Okay? I'll be happy to help you with the assignment. In conclusion, we arrive at these conclusions. VT-NMR is useful to study dynamic processes such as conformational dynamics, restricted rotation in a molecule, molecular rearrangement, molecular association in solution. So I gave examples for each one of these. And then it's possible to obtain rate constant, equilibrium constant of such processes, deduce the relevant thermodynamic parameters from such NMR studies. Don't feel shy to speak in English or in Tamil. With me, you can speak in Tamil. I know Tamil quite well. If you want to speak in English also, it is fine, but don't be shy that you will make mistakes. I came from Tirunelveli to Chennai to do my MSc. At that time, there was a telephone in the hostel. It is the first time I have spoken in telephone. Nowadays, you guys play with the cell phone left and right. But at the age of 20 or so, first time I took the telephone and said hello. It was a scary experience actually to speak in a telephone. But now I am in a better position. I am able to speak to an audience of like yours, for example. So don't give up easily. That's what I would like to advise you. Wish you all the best. Have a pleasant stay here. All the best wishes to you.
SwayamPrabha. Digital India. Educated India.